Uh, okay, so we will start now. We waited for some time for people to join. I think Sanjay is here and Krutika, maybe, if I'm taking the name correctly. Uh, I have muted myself. And yeah, so welcome to the discussion for the 12th week assignment. Uh, so basically, uh, this time, like this discussion will be mostly revolving around the statistical progress control because uh, like we started some part of it in the last class, but mostly uh, this will be related to the different techniques that are used in statistical process control, which is SPC. So first of all, uh, this statistical process control. So it is nothing but the short form we will use is SPC. So basically, the purpose of this, what is the objective of this process? As the name suggests, it is a statistical method. So it relies on different statistics of data that we collect usually by running the uh, process or maybe whatever like manufacturing process or any other type of process we run it, and then we get the data, which is nothing but the statistics, and then as the last word, which is control. So that means whatever data you have, you use it to control the machine going forward. So that is the main crux of this statistical process control method. And so since it is a control method, it is uh, used to uh, used to measure, understand, and control variation in a manufacturing process. So this objective should be clear before we discussed anything. What is SPC? It is a statistical tool with the help of which we can measure, understand, analyze, and control the variation in any manufacturing process. So that is there. And after that, uh, there are some assumptions using uh, before using this method. So uh, what should I use? Maybe I'll use circle or something. Yes. So there are assumptions. So these assumptions, if you know, you will not get caught off guard. For example, in the one of the video lectures, professor was discussing that there should not be trend in the data that you are getting. It should not be like positively increasing or negatively decreasing, or maybe cyclical or something like that. It should not have any bias. So basically, it should be a completely random data. So that is one of the assumption. Uh, so like uh, variation in process, like the process that we are uh, going to study, variation in process is random. So there should be no trend, bias. What else? There are some. 1 second, I'll just list down those things. and shift, etc. So in the data that you are going to get, you assume that it is a random distribution. So that's why we use Gaussian distributions. Later you'll see that we use this 3 sigma, 6 sigma, and all those things. So uh, you can define a Gaussian distribution, which is nothing but the distribution which is used for describing a random process. And you can define the Gaussian distribution for that random process using only two quantities, which are nothing but mean and the variance. And standard deviation is like square root of the variance. So basically, that is why if you had paid attention uh, in the class, lectures, you would have realized that one quantity, that one of the methods or charts that we use, it deals with the mean of the sample deviation or the sample data, and another chart, which is R chart, that deals with the spread or the variation or variance or standard deviation of that data. Maybe we'll talk about them going forward, but just keep in mind that we assume that the variation is random, and therefore uh, this helps us to use, therefore we can use normal distribution. So this you should know. And second assumption, which is like important assumption, is this method assumes that uh, whatever you do, uh, like there will be this thing, what you call, uh, 1 second. Uh, see. So any natural process will have some sort of variation. So this is the second assumption, that no process is where, like, there is no process in the universe, or as far as human beings are concerned, uh, uh, which will have zero variance. There will be somewhat variation because of natural causes or the causes which are not in your hand, and that variation is acceptable. But the variation which is caused because of some certain special reasons, this is called as assignable causes in this context. So if such variation is there, we can control that variation, and only that we can control. So uh, this like for this analysis, the second assumption is there will be some variation in in each process. So we don't assume that we can eliminate the variation completely. We just assume that there will be variation, but we should keep it within the allowable limits. So which is, if you had studied this, there is one field of science which deals with this variation and how to control that. This becomes especially important in the field of surface roughness, etc. So there are different standards of surface roughnesses. You can Google it, or maybe Chat GPT it nowadays. So there, this I think it is called as when uh, I'm forgetting. It is a science of measurement. Basically, there is a one word which is similar to measurement only. There it uses. There it is important. Similar these charts that we are going to see now. They are used there also. And the basic crux is whatever you do. We are primarily talking about manufacturing industry here. So whatever you do and use whatever type of tool or material or whatever you want, but you cannot reproduce same component exactly. So if you reproduce something using some machine, the next component will be different from the first component, and there will be slight variation which may not be visible to our naked eye at times, but there will be some variation, and our objective is to keep that variation under the acceptable limits. So that is the whole uh, whole discussion here. So now, why do we, like, obvious question is, why do we want to keep the variation in limit? It is because if you keep it under limit, it will be more acceptable. Like more number of product components that are produced by you will be acceptable because they are in a they conform. Basically, the conform is also one important word used in this context. So they conform to the specifications given by the uh, customer within some acceptable ranges. So that will reduce waste, reduce cost of production, material cost, everything, and that will be helpful for your business. And now there are like two type of variations. So I'll just put it here. Maybe this word which we are saying, there will be some variation. So there are two types of variations that we consider here. One is random variation. So this is like because of natural causes that you can't control. So this is not under control. This is also called as chance or something like that. They use chance variation or common variability, something like that. But this is the random one which you don't control, which you can't control. And then there are some assignable variations. Or aka you can call them as special variations. So these, the whole objective of this discussion is to control these. So, oh, 1 second. We can control this, and that is what we are going to see. That, like, first of all, to control something, you should know what is going wrong there, or is it not under control. So some techniques are there that we'll see, but before that, you should know. And see, these random variations are inherent, natural. You can't do much, but the special variations which are because of different parameters, mostly you can just if you want to remember why this happens, uh, these usually happen because of man or operator. So the person who is operating the machine which produces the desirable component, if that person is knowingly or unknowingly doing some out of the way things during the manufacturing, then there will be special variation. Then next is method. So like, you know uh, if you, instead of using given method, if somebody is using another method which gives the production in lesser time, but that will be compromising some other aspect of the design, and therefore you'll have variation in your final product. And then this material. So whatever raw material or whatever other auxiliary materials that you use in the production, if they are not up to the standard, or if there is a variation in their quality, then it will be reflected in your final quality of the finished goods. And then there is machine. So these are like the famous 4 M's in this subject. You might have listened or studied these in previous lectures and classes. So by machine, you specifically refer to the tools and machines that are used in the production process. If the tools are, see, tools will wear out periodically. So that variation will also result in the variation in the finished goods. So you need to make sure that you did proper maintenance of tools, machines, etc. Measuring devices, for example, scales, weighing scales, or you know, length, something like that. So these are the causes that we want to control. So now going forward, I'll take some basic questions so that you'll have some idea that what we discussed is not that trivial, and this is like the uh, foundation of this discussion, and many questions can be asked from this. So okay, I'll take one question here so that we will have some variety. Otherwise, the whole theory will become boring. So question is, maybe I'll use different. So control limits in process control charts or chart is defined by, or maybe you can put like is decided by. So first option you have by customer, second option you'll have natural variability of the process, uh, then you'll have uh, maybe statistical limits, statistical limitations, and then you can have something like uh, operator skills. So there may be some terms that you don't know now, but let's say control limits, as the name suggests, it is the these are the limits which you set for the variation for any process. And control chart we'll see in some time, but just for the sake of discussion, control chart is a, it's basically a graph. And so coming back to the discussions that we did so far, so what this question is asking is, for any process, when you use this SPC and when you set the control limits are decided by what factor? First option is customer, second is natural variability, third is statistical limitations, and fourth is operator skills. So can anybody one of you give me the answer to this question? I'll just have some water in the meantime. Maybe Ganesh. I'm audible, right? Okay, Ganesh has given the answer. Uh, I don't know why when I use the tab, I don't see the messages here. Maybe how should I do this? Okay, I'll open my chat box on my mobile. Yeah, so Ganesh is saying the answer is 3 option. So that is correct. So basically, whatever control limits you set, uh, they are driven by the natural variability of that process or this random variation that we discussed. So therefore, that will decide the uh, control limits. And see, customer can't decide the control limits because customer will give you some specifications and you need to follow that. But how to be within those specifications, that is under your hand, and that is the minimum that you can do is the natural variations. You can eliminate all the assignable causes by properly taking care of things, but natural variations you can't do anything about. So that's why they are the limiting criteria. uh, then so such a okay, I'll take one more question, which is uh, maybe we can discuss this, but okay. So the process chart that I was telling you right some time back, or maybe for this question. So what happens? Uh, on the x-axis, you will have the sample number. The sample number is basically uh, let's say you are producing the finished goods, and to get the statistical data, what you do, you take some samples out of the finished goods. So that is in your hand how much number of units you want to keep per sample. Let's say you are making a sample of 5 units, so you take 5 units, that is your one sample. And what you do, you, like on x-axis you plot them. So this will be first sample, second sample, like that, and so on and so forth. So you will have sample numbers on x-axis, and on y-axis you will have limits. So the limits you will set, control limits as they are called uh, vaguely here. I will explain more in the detail, but for the time being, just let's assume that there are some limits that we set and we want to adhere to those limits. We want to keep our variation within that limit. So there will be something called as mean. So for each sample, you will, okay, before going there, uh, there is something like these control limits are set for what parameter. So uh, like there are two types of characteristics of process. uh, so like, I mean, if I tell you uh, you need to control something for a post process, you should know what to control, right? So there are basically two classes. One is called as uh, the characteristics of process can be divided as variables. These are like, uh, you can measure them. These are measurable quantities, like, let's say, length, weight, uh, volume. So the quantities you can measure uh, are called as variables. And then there is another category uh, of characteristics of any process, which is called as, one second, yeah, so there is one more category which is called as attributes. So attributes are not measurable quantities. They are like qualitative qualitative characteristics. uh, Maybe I can write example here: length, weight, etc. Whereas attributes can be smell, uh, defects, color, etc. So by color I mean appearance. So there can be texture also. So the quantities which you can feel but you cannot measure, you can count them. So like, you can, one second. These attributes are not measurable but countable. So you can remember this way. Maybe this will help. So uh, this is important. And now once see, now you have to choose whether you want to do the controlling using any variable or any attribute. So uh, you can choose variable also or any attribute also. There is nothing wrong in that. It all depends on what process you follow or what is the nature of process that you are observing. So coming back to this discussion of the control limits, so here you will choose a particular characteristics for the process, and then you will do the sampling. And for each sample you will have its average, you will have its range. uh, Average is nothing but the you take the sum and divide by the total number of the units in that sample. And range, as the name suggests, it is the difference between maximum and minimum quantity in that sample. So you will plot mean of each sample. Like for all samples you'll take mean and you'll plot mean of mean. So that is this red line. And then you will have some mathematical formula or something like that which will decide your upper limit and lower limits. So this is your UCL and this is LCL. So basically it is lower control limit, and this will be your upper control limit. So this will define your range of variation. So you, whatever you produce, you need to stay between these two blue lines. So these blue lines, if you consider this, that the width that is between the blue lines, this is called as the random variation, which you can't do anything about, random variations. Whereas these things, like the variations which are out of the bounds of the control limits, they are called as uh, assignable variations. So this itself is a one question in one of the, I mean, the one of the questions that I came across. The question, I'll just read it out. I think I have given the answer directly. So, so the question is, in the control chart, this whole thing is called as control chart. Okay, this control limits versus sample number. Now we will see in some time that there are different methods to uh, you know depending upon whether you are analyzing a variable or an attribute, there are different types of methods that you can use. And to set this UCL and LCL, there are different types of methods that you can use. So that we will see in some time, but uh, just understand that by doing any method calculations, what we are going to get is control chart, which looks like this. On y-axis you will have some limits, and on x-axis you will have some sample numbers, and your objective is to stay within these blue lines or the control limits. And if you observe that any data or any sample is crossing these limits, that means there is a abnormal behavior due to assignable causes. So then you can address that. So you need to see what type of error is, like what type of abnormality is that, and from where it is coming. So there are like four sources for that abnormality, right? Man, method, material, and machine. So if you see that your process is not under control at some points, then you go back and you check those samples, and you figure out from where this abnormality is coming, and why the why your system is not under control. So this is how it goes. We will see the different methods, but one question. Uh, okay, I'll just write it down for those who are not attending live. So the question goes like, in control chart, uh, data points beyond control limits are called as, first option is abnormal variations due to assignable causes. Mm, then the second option is abnormal variations due to central line. Then there is normal variations due to chance. And the fourth option is normal variations due to process distribution. So if you had paid attention to whatever I just said for last 5-10 minutes, you will easily understand what this answer should be. So can anybody just give the answer? Maybe you can type it out. I can see the text now. Yeah, so first option is correct. Yeah, so I mean, I had given you the answer first and then I asked the question. So, but anyway, so that means you are listening to whatever I'm saying. So basically, see, the answer is clear. I'll just talk about the other things. So second option is abnormal variations due to center line. This doesn't make any sense. This is just a random option to confuse those who don't know what this is. Uh, you may see this in many competitive exams like GATE or maybe ESE or something. Uh, if you know at least what that question is trying to answer, then and there you can eliminate two options easily. Finally, it will come down to two options that you need to choose one of them. Here also, this second option, which is abnormal variations due to center line, it is a random thing. There is no meaning to this for this context. And the last option, normal variations due to process distribution, that also doesn't make any sense. So option first and third are the only competitive options for a correct answer. Third option is normal variation due to chance. So that is not beyond the control limits, that is within the control limits. So therefore the first option is correct. So just make sure that whatever words or whatever terminologies are introduced in any course, not only in this course, you are, you should at least have some idea that what it means. Then only uh, you can answer anything. Otherwise, you will be confused and they will confuse you like this only. So anyway, moving forward. So now, uh, okay, so there are like different types of charts, control charts. So to remember it, I can just give you one tree diagram because this is also confusing, and this itself will have a potential of maybe one or two question in GATE exam if they want to ask. So as I said, there are two types of characteristics. First is variable and then there are attributes. So depending on that characteristic, the control charts are different. So for variables, there will be different control charts, and for attributes, there will be different control charts. So for variables, you have mean chart, which is called as X bar chart, and you have range chart, which they call as R chart. And for attributes, you have, let's say, P chart, you have NP chart, and you have C chart. So this mean chart and all will take some examples, but this N, NP, and C, this itself can be one question for this thing competitive exams. So I'll just give you full form here. Maybe we can discuss them later. Uh, just give me some time to find the full form. I don't want to make any mistake here. They were here somewhere. I'm not sure. 1 second. Give me some time. I'll find them. Yeah. So uh, maybe I'll use some different color. So P chart is for proportion of defectives or non-conformatives, whatever you want to call. So from P you can remember P is for proportion. So maybe you can call it proportion or fraction, but P chart you will have as a proportion of defective units, or yeah, like that. And NP chart is for like number of defectives. So it starts with N, so you can remember it as the number of defectives. And C chart, this is for number of defects per unit. This is not defective, okay? So this is like number of defects. So you should remember this. And this 3 red lines itself can be 3 questions I can ask on them, and I can increase the number of questions in the discussion, but that's not the point here. I'll just read out one question. Maybe you can just type in the comment section. So the question is, a control chart used for monitoring attributes like many number of conforming non-conforming units in a sample is. Okay, I think it's too long. I will write it down. So the question is a control chart used for monitoring attribute which is number of non-conforming units in a sample is. Option 1 is C chart, second is P chart, third will be NP chart because we have these 3, and then there will be some X bar chart. So can I mean answer is here itself only. Oh, still somebody said third option. So okay, NP chart. Yes. So because you are counting what you call number of non-conforming units. Non-conforming is, I mean, this word, it's just a fancy word, but it is equivalent to saying defective. It is synonym. So they will just confuse you with this fancy language. If you don't know what is conforming means, then you will not know what is non-conforming means, and then you will be stuck. But so basically conform means to stick to or to adhere with. So that means if you conform with something, that means you stay with that thing or that ideology or something like that. So when it says non-conforming, that means it is not sticking to your standards. That is what we call as a defective product or unit. So here the correct answer will be NP chart. So like that I can ask 3 more questions here only. Okay, so but that is just consuming the time that you can. If you remember this red lines, 3 lines, you are prepared for 3 questions, don't worry. So now next is so for variables and for attributes you have different charts. So we'll start with what you call variables, but before that something about normal distribution. uh, so normal distribution looks something like this. It is a bell-shaped curve, not like this. This thing modified itself. So anyway, uh, like you have this x-axis which is like number of samples. Anyway, so then you will have some mean for your data. This will be your mean, and then you'll have something like this. it is a bell-shaped curve. Okay, so don't like forgive my uh, improper drawing. It is a symmetrical curve about mean. It should look like that. I'm not drawing it properly because of human error. If I try to draw it very carefully, it will automatically make it some random shape. So that's why this is thing. So then there is something called as this is a Gaussian, or you can call it as a normal distribution. This is a unimodal normal distribution. It has only one peak. There can be multimodal distributions, but that is not part of this course. So, like whatever data you will have some mean, right? And half of the data points will be lower than that mean, and half of will be uh, more than that, right? That's why it is average. And then there will be something called as variance, because as I said, the Gaussian distribution is defined using two quantities. One is mean, second is variance. But here, this is equivalent to this standard deviation. I mean, it is just a square root of variance, okay? So we use this sigma as the symbol. So, like if you call variance with the symbol V, I should not say equivalent, because like variance or standard deviation, and variance is nothing but sigma square. So they are like same quantity, only differentiated by a square root sign or symbol or operator, sorry, square root operator. So variance is nothing but, as the name suggests, is the spread or the range. So there can be one normal distribution with this type of 1 second. So if you calculate this standard deviation for this curve, so what you say, I think it encompasses 67% of the data. Let me just confirm it once. 1 sigma standard deviation. Yeah, so it can encompasses. Okay, I will draw that figure only because that will help us in future. So maybe I can put some more lines. So this is only schematic, okay? Don't go by scales or length given here. So the center line is the mean line that you know, and sometimes it is denoted as by mu. Maybe not here. Will not use mu symbol. So maybe I can remove it. I don't want to cause any confusion. Okay, just let's say it's a mean. Then there is, this is 1 sigma positive, 2 sigma, 3 sigma. Similarly, 1 sigma negative, 2 sigma negative, 3 sigma negative. So what it does is it gives you some idea about the number of data points that will lie within this region. So if you take uh, 1 sigma deviation or variation, which means you take +1 and -1 sigma around the mean, then you will observe that uh, ±1 sigma, uh, it includes I think 67 point something. Let me just get yeah, 68.2. It includes 68.2 percentage of all data points. Similarly, there will be, I can just copy paste now. Okay. Hmm. this thing started. I don't know. Sometimes it pastes, sometimes it just doesn't work. What is wrong? Anyway, I'll just write it out. And for 2 sigma, this number will be approximately 68.2 plus. Oh, it was given in the lecture, right? Yeah, it is 95.44% of all data points, and for plus minus 3 sigma it is up to 99.74%. The reason I am giving you this number is when I was preparing for GATE, this question was directly asked in the GATE exam that for 2 sigma how much data points it encompasses. So this is like a factual question. If you know, you know, otherwise you don't know. So I should have used some other color, right? Anyway, but you understand, right? 1 sigma, 2 sigma. So basically, when you say that your Gaussian has 3 sigma deviation, that means you are considering out of 100 data points, you are almost considering 99.7 data points. So you are not leaving much data out. But if you are just considering 1 sigma deviation, that means you are only considering 68% of the data points and you are neglecting the remaining 32%. So this is what it means. With like, so I hope mean and variance is clear. So if your normal distribution has a smaller variance, maybe I can use a different color in this figure only. So there can be another normal distribution like this, which has same mean, but the spread will be smaller. So one second. So this is normal distribution with lower variance or sigma or standard deviation. This question was also again exactly asked in the GATE exam. One of the mechanical previous year question papers. You can go and check. That is the reason why I'm spending this much time on this. Otherwise, I could have just taken 1 or 2 questions and be done with it. But that is not the point, and that will not help anybody. So anyway, so I thought this information is important to know. So I mentioned it here. You can refer it. But just keep in your mind that uh, like when you say 1 sigma, it is around 68% of the data points. When you say 2 sigma, it is 95%, and 3 sigma is 99%. So at least if you remember this, you will be okay. And one more note is for normal distribution, mean is equal to median is equal to mode. So all 3 quantities are same. This is only for normal distribution, okay? For other distributions, these are different. You can check them out. Any probability course introductory book will have these in the first chapter itself, because there are different type of distributions, right? One is normal, which is Gaussian. Then there are like exponential distributions, Bernoulli distribution, uh, you know, many distributions are there, like skewed beta distribution, alpha distribution, many things are there. But for this course, we only bother about normal distribution. So that is like a reading exercise. If you're interested, you can go and check. So yeah, so we will go with the first, like as I said, for variables there are 2 types of charts, mean chart and range chart. So we'll go with the, we'll take one example where we have mean control chart for a variable. So let me just see the data. One second. Mean control chart. Okay. Okay, so we'll take this example. Control chart for a variable, and this is like that. So this is like mean of mean, that type, not a range. Range one will be similar, but here we are taking only uh, first we are taking that X double bar chart. So here what you do basically, I'll give you the question itself, so maybe that will be better. In a mean control chart, mean of 4 samples are 10.15, 10.20, 10.11, 10.34 under 9 observations, and the process standard deviation is given as 0.03. Now find UCL and LCL for sigma means. So this is a typical question that is asked from this type of this thing. So now you have x1 bar, which is first mean, which is 10.15, x2 bar, which is second mean, which is 10.20, x3 bar is 10.11, and this is 10.34. So now as this is a mean control chart, what you have to do, you have to take the average of average. That's why the double x bar. So that will be 10.15 plus 10.20, 10.11 plus 10.34 divided by 4. So this will be 35 plus 45, which is 80 by 4, 20. So it will be 10.20. So this is your average of average. So this will be the mean line, okay? The line that I showed now here, the red line. So that red line on y-axis, it will have the value of 10.2 in this question. And now it is given that sigma is 0.03 and number of observations in one sample are 9. So n becomes 9. So therefore this sigma x, which is given by this formula, if you do the calculation, it will be, so I mean there is no need to put sigma bar x because this is like sample mean, and then the UCL is calculated as you can put it because this is for averages. Then therefore UCL, the formula is x double bar plus z, some constant, which is called as standard normal deviate, but it's a constant, so no need to bother about that much. So here x triple bar is double bar is 10.2, and in the question it was said that 3 sigma means you have to calculate. So this is z will become 3, and this will be your 0.01. So this comes out to be 10.23. Similarly, LCL will be, only there will be minus sign here. It will be 10.2 minus 0.03, so this will be 10.17. So now you go back and see. So these are your limits, right? 10.23 and 10.17. So okay, since we are here, I'll do it for one thing. So you had like 4 samples, right? 1, 2, 3, 4. You calculated mean, which was 10.2. Then you calculated UCL, which is 10.23, and LCL, which is 10.17. And now you can plot your x1 bar, x2 bar, x3 bar here. So one is 10.15. I'll use let's say black color only. So first x1 bar is 10.15, which is lower than LCL. Then second point is 10.2, which is like exactly at the mean. Then you have 10.11, which is again below the first point only. And then there will be fourth point, which is 10.34. So this is out of the upper limit. So now you can see here only one point is within your control limits. So clearly your process is out of control here. And now see, 3 points are out of the range, 2 are below the range, 1 is out of above range. So this is like completely out of control system, and you need to do more work and find the root causes for this behavior. So this is the whole point of doing all this exercise, that whatever you are doing, you should at least know that, like, it should give you an indication that your process is in the control or out of the control. So I hope this is clear. Now this is the mean chart. Similarly, you will have a range chart. Uh, so range chart is basically what you do. So okay, I'll just give you some broad idea because the calculations are similar. Okay, so this one was control chart. Then we have range control chart, which is also called as R chart. So here the difference from the previous one is, here UCL is nothing but D4 into R bar, and LCL is D3 into R bar. So here you don't calculate all those things like X double bar and all. Here you calculate only R bar. So now the question is, what is R bar? And D4 and D3 are constant. Okay, these you will get from some standard tables are there. You can look at any textbook and all. You'll find these values for Gaussian distributions there. You should know that one note here is, as n increases, which is the number of units per sample, your D3 and D4 decrease. So this is to understand the reason behind this, you should know how the standard table is derived, but that is not the part of this course. So here you just keep remember this like a formula, that if you are higher number of samples in higher number of units in your sample, then your constants will be having lower value. So that is one thing. And here you don't calculate x bar and all. Here you just calculate r bar. So one second. I'll take one small example, but I mean, we don't have that much time left. So I'll just explain. If you have any doubt, you can ask me. You can type it out in the comment section. So basically, here instead of calculating x double bar, which is average of means, here you calculate range for any one sample, and as the range name suggests, it is difference of minimum observation and maximum observation, and you do it for each sample, and you take average of that range values, and that is what is r bar. So r bar is nothing but average of range values for all samples. And then once you have r bar, once you have D3 and D4, which you get from a table, depending on how many number of units per sample you have chosen, you can calculate UCL and LCL, and similarly you can plot graph like this. Here red line will not be there, okay? In red range control chart, there is no mean or something. There is only UCL and LCL. So only two blue lines will be there. And then what you do, you don't look at the, okay, I think I should draw one because this is slightly different. Okay, I'll take one example quickly. So here you have 4 units per sample. So like that you have this is the sample number. So you have a table like this. Maybe I should have extended it. So you have table like this. So these are the sample numbers, and you have the data, which is like for each in each sample you have 4 data points or 4 units. So you have this data. I'll just quickly fill it because there is no point in spending time here. Okay. So now what you do, instead of taking average and all, what you do, you just find out the range for each sample. Here it is 0.03 because minimum is 0.08, maximum is 11. Here it will be 0.04. Here it will be again, no, it will be 6 here. Here it will be 4. So now you take the average of this, which is your R bar. So average of 3, 4, 6. So 10, 17. 17 by 4 will be 4.25. So average will be 0.0425. I am leaving this exercise to you. I hope you can do this. And then here n is 4. So you go back to the table and you get the D4 value as 2.28 and D3 as 0. Usually we don't take negative values for D3 and D4. So if the table gives a negative value, you just take it as 0. So therefore UCL will be D4 into R bar, which is 2.28 into 2.28 into R bar is 0.0425. So this is 0.097. I'm right, rounding it off. And LCL will be equal to 0 because D3 is 0. So here, if you want to plot the R chart, it will look something like this. You will have 1, 2, 3, 4, and you will have UCL and LCL. There is no concept of R bar here. So this is your UCL, which is 0.097, and your LCL is 0. And now for the first data point, your range was 0.03. Okay, so you only plot here R. You don't care about this 12 and all. Only R you are bothered with, which is range. So for first data point, the range is 0.03, which lies between this. It should be somewhere here. Then 0.04 again somewhere here. 0.06 somewhere here. 0.04. So here your all points are within the control limits, therefore your process is in control. So like that you have to do. So this is your R chart. So usually we don't use them separately because like there is one more note here you should know. This was I think discussed in class also, one of the lectures, that this mean control chart it is sensitive to the this thing, sensitive to shifts or shift in the process mean, whereas this thing, this range control chart, it is sensitive to spread of the process. So what this means is uh, mean chart, like I mean there was this example given in the class. If I start drawing it here, we will not have enough time remaining. So see, your process mean can go up and down, right, depending on the data, statistical data that you collect. So if you are using only mean chart, you can capture the variation in the mean x double bar that is going to change, but you will not have the idea about R range. So and if you are using R, which is a significance, like the equivalent to the like spread of the data of that process, then you will not capture the mean, because as you notice here only, for a range chart you don't plot mean, there is no significance of mean. And for R chart there is no significance of sorry, for mean chart there is no significance of range, and for R chart there is no significance of mean. So therefore you have to use both of them together for your data. And if your process is within the control limits of mean control chart as well as range control chart, then only you can say that your process is under control. Okay, you cannot say based on only one. So that is the key takeaway. Then this is regarding the what you say, these are the variables, the like mean and range chart for variables. Okay, so similarly there will be this control charts for attributes. So as I explained earlier, this P chart, NP chart, C chart, so they will be for attributes. So attributes are characteristic of process which you cannot measure, but you can count them. So like number of defects or number of non-conforming units in a sample, something like that. So for that also there are some what you say formulas. So you collect the data and uh, use some formulas. I can give you them, but you know uh, it is not a value addition from my side. Okay, you can just go to the class notes and see them, and maybe you can go through some problems. Since we have limited time, I'm not going through it, but you should solve some problems and get some idea. So for P chart, what is there? I'll just give you the formula. So for P chart, what you do, UCL is calculated as P plus Z into sigma P. Now you will ask what is P, what is Z, what is sigma P. Z is same as earlier. It is like 2 sigma or 3 sigma. So if it is a 3 sigma limit, you take Z as 3. If it is a 2 sigma limit, you take it as 2. P is a fraction of defective items in the population. Since it's a P chart, right? So it is a P stands for proportion or fraction, as I mentioned earlier. Proportion or fraction of defective items in population. The like total number of uh, samples that you had. And this sigma p is calculated as 1 second. Sigma p is calculated as p1 minus p by n. So the whole thing that and then similarly LCL will be p minus z sigma p. So here the whole thing is to find p. How you find p? So maybe we can take one example about this. 1 second. Let me just look for it. So let's take it in the form of question. For like I'm skipping the additional parts. So there is a company which produces some A type of product, and for that product we did a sampling, and we are using attributes for that product, not the variables to characterize the process. So therefore we need to use control charts for attributes, and in that also we are using P chart. Okay, so this is relevant for this example, this chart type. So the question is total number of defective units is 200. This is the data, and observation was taken 20 samples, like total 20 samples we took, each containing 100 units. Okay, then find UCL and LCL for 3 sigma limits. So this is a typical question that is asked from this context. So here the only catch is how to calculate P. So P, as the name suggests, it is the fraction of defective items in the whole population. So there are like 200 total defective items. And what is your total population? You have 20 samples and each sample contains 100 items, right? So total you have 2000 items. So this is 200 by 2000. So this is 0.1. So this is your P. And then now everything becomes easy, right? Because, okay, before UCL we calculate sigma P. That will be 0.1, 21 minus 0.1 divided by n. N will be 100. And now if you do this calculation, it will be 3 into 10 to the power minus 2. So 0.03 it should be. 0.1 into 0.9 minus 2 minus 4. Yeah, so it should be 0.03. And then you can calculate UCL as 0.1. And this is again 3 sigma. So you will have 3 here and 0.03. So it is 0.09. So it is 0.19. LCL will be 0.1 minus 3 into 0.03 will be 0.01. So this is how we solve. Now you can again go back and draw XY axis, and for 20 samples you can plot this UCL and LCL, and now for each sample you check what is the P value there. So then you plot it, and then you'll get a idea whether your process is in control or out of control. Understood? So like that you can do there. Now again, next we will have this P chart is done, right? So you will have C chart, sorry, NP chart and then C chart. But this thing more or less this is same only. You know this thing for C chart what happens? C chart is you know uh, like this thing what you call uh, it is total number of defects per unit, right? It is not the proportion or anything. It is an absolute number. So there the formula is slightly different. Uh, I can just give you, but this is already in the notes, class notes. You can just refer them. So for C chart, uh, C represents number of defects per unit. So here you don't take any ratio or anything. It is an absolute number of defects. And here you have UCL as C plus Z into root C, and LCL as C minus Z into root C. So like that you go ahead with this. I can take one example, but I don't think we have time. So one note you can take here is what happens is sometimes what will happen when you do the subtraction for LCL, which is like C minus Z root C, or for P chart also, which is like P minus Z sigma P. Then sometimes it may happen that if LCL becomes negative after subtraction, you just take LCL as 0. So that is the lower limit that you can set. And that's how you go ahead and solve these problems. So there is one last thing that is remaining. Uh, yeah, so there is something called as process capability. So here instead of UCL and LCL, maybe I'll just briefly discuss this. Process capability. So till now we were talking about process control, okay, but this is slightly different concept. Here what you do is like uh, instead of you know setting control limits which were like UCL and LCL so far, what you do here is you take the specifications given by the customer, and whatever here it will be upper specification limit which is called as USL, and then there will be some lower specification limit. So this will be provided by the supplier in this case. Okay, this is not your job anymore. So if this will be LCL. So here what you do, uh, you know, some graph, something like this will come in this case. So you will have your variation from your process, right? This thing, I mean, I need to draw it badly, then only it will keep it. Anyway, so you will have some variation like this, okay, which is your process variation, and then you will have your specification limits. So this will be your maybe LCL and UCL, and here the x-axis is not what you say number of samples or something. It is like that characteristics itself. So one second. Yeah, so on x-axis you will have this. Let's say we are comparing a diameter of the specimen, and this the customer says that the specification expected by him is uh, let's say 10 plus minus 2 mm. So now uh, this will become your U. I put LSL, I should have written. UCL is previous thing. Here your USL will become as per the requirement, which will be 12 mm. Here it will be 12 mm. And your LSL will become this 10 minus 2 will be 8 mm. So it will be 8 mm. So now what you do, you just start producing, and this will be your mean somewhere like here. So this will be your 10 mm target. So what you do, you start producing and you take the dimension of like or the diameter of the finished product one by one and plot it here. So you will get distribution like this, right? And we are assuming that it will be a random distribution, and most likely it will be. So as long as this spread of this is this distribution, let's say these are your uh, 3 sigma limits. So this is your minus 3 sigma, and this is your plus 3 sigma. So as long as your 3 sigma limits are within this LSL and USL limits, then that means your process capability is good. If it is falling out of this range, then there is some issue and you need to rectify that. So that is how it goes. So this is like the brief thing. You can look into more about these things, but since we don't have enough time now, and then there is a last thing. This is something called as what you say, uh, you know, mm, method study and other this productivity and other part. I mean, it's not that difficult, but the only thing that you should remember out of that context is I'll just give me some time. Uh, that part you can just that's mostly theory. There is no numericals there. Some one-liners can be asked from there. So there is something called as uh, you know what you call that name I'm forgetting. There is something called as uh, one second. You know, work measurement, method study, etc., etc. So here the only thing that you should remember is when like these are the tools by which you can increase your productivity of your organization or something, or maybe process, whatever is your target. But whenever somebody says work measurement, that means it is a quantity based approach. So basically you will have some measurements because the name itself says measurement. So you will have some technique with the help of which you will measure that, uh, maybe if you want to increase the efficiency, or you want to reduce the idle time or something, then you will use some techniques where you measure the data. So that is what work measurement is. It has different techniques like time study, work sampling, etc., etc. We are not going into details of that, because it was not, like, it is not in the purview of this course, as well as we don't have time. And there is something other which is, I think, called as methods, study method or something like that. That is a qualitative approach. There you don't use these things. You don't do any measurements or anything. You just take qualitative guesses or qualitative observations, maybe the correct word, and then you go ahead. And like, for example, if you have a process, and you know you this thing, what you say, uh, one second, that word is not coming in my mind. One is work measurement that I told you that, the other one is method study. I'll just briefly write here, like these are the like tools to increase the productivity. So related to the productivity, uh, one is called as method study method, I think. Method study, okay. MS. And there is something called as work measurement. So here it is a qualitative thing. So you don't do any measurements here. What you do observations, and then you propose that this process, if you change it this way, or if you make this modifications, then maybe your efficiency or productivity will go up. But work measurement, it is a quantitative thing. Here you take quantitative measurements, you use quantitative techniques. Example, what you say, this time study, etc., etc. I mean, if you are interested, you can look into this, but not the part of this course as of now. I'm just giving it so that if any any one-liner is asked, you can answer this. Work sampling, etc. There were 2, 3 more names that were given by professor in the class. You can look at the lecture, and then so that's how you go about it. Okay, so I think I have covered all of the topics that are to be covered now, and today it's slightly elongated. So maybe if you have any questions, you can ask. Otherwise, we can stop here. Anybody?
No, sir.
Okay. Sanjay is happy. So if nobody is having any doubt, we will stop here. And I think this is the last lecture for this course from my side. So Sanjay, okay, he muted. Okay. Okay, so this is like the last lecture from my side for this course, and I hope those of you who attended it or maybe watched it later, some sort of knowledge addition was done, and that was my whole point. Uh, I usually don't follow that method where you just start taking the question and do that. I like to discuss some concept and then take questions related to that. So that is what I do, and that is what I did for this course also. So thank you for your participation, and stop now. Maybe we'll meet
Thank
later.
you, sir. Thank
Okay,
you, sir.
thank you.
Thank
Okay,
you, sir.
yeah. Ganesh was quite silent today. Anyway. So, Ganesh, you want to say something or shall we stop?
Nothing, sir. Thank you so much for your classes, sir.
Okay, yeah, thank you,
It's
Ganesh.
good to have your classes. Thank you.
Yeah. So, okay, then if no question or anything is there, we'll stop now. So, good night and take care. Bye.
Good night, sir.
Yeah.